How does reliability engineering prevent failures in spacecraft? Imagine a spacecraft soaring through the vastness of space, where every second counts and every component must perform flawlessly. How do engineers ensure that these complex machines do not fail? The answer lies in reliability engineering. This field focuses on designing, testing, and managing spacecraft systems to ensure they function as intended throughout their missions. At the heart of reliability engineering is the concept of design for reliability. This means creating systems that are robust from the start, rather than relying on fixes after the fact. One key principle is simplicity. By reducing complexity, engineers lower the chances of failure since simpler systems have fewer parts that can malfunction. Another important aspect is redundancy. Critical components are often duplicated or even triplicated. This ensures that if one part fails, there are backups ready to take over without disrupting the mission. For example, if a power supply fails, a backup can immediately provide the necessary energy. Fault tolerance is also essential. Systems are designed to continue functioning correctly even when some components fail. This is often achieved by switching to backup hardware or software. Derating is another technique used, where components operate below their maximum limits to reduce stress and extend their lifespan. To identify potential failures early, engineers employ techniques like failure mode and effects analysis. This method examines how each component might fail and the impact on the spacecraft and mission. By prioritizing risks, engineers can design safeguards to mitigate them. Fault tree analysis helps analyze combinations of faults that could lead to system-level failures, guiding improvements in design. Once the design is complete, spacecraft systems undergo rigorous testing. These tests simulate space conditions, including vacuum, radiation, and extreme temperatures. This helps reveal weaknesses that can be addressed before launch. An essential part of reliability engineering is fault detection, isolation, and recovery. Spacecraft are equipped with autonomous systems that detect faults, isolate the failed components, and recover by switching to backups or reconfiguring operations. For instance, NASA's Mars rovers have fault-tolerant designs that allow them to continue missions despite hardware failures by automatically switching to redundant systems. Verification and validation processes ensure that all hardware and software meet strict safety and reliability standards. Independent teams test and verify that systems behave as intended under all expected conditions. Reliability engineering also integrates with fault management systems that monitor spacecraft health in real time. These systems execute pre-planned responses to anomalies, often without ground intervention. This autonomy is crucial since communication delays can make immediate human control impossible during many space missions. Practical applications of these principles have been demonstrated in missions like the Mars Curiosity rover and the Parker Solar Probe. These missions showcase how expanded failure mode and effects analysis and autonomous fault management enable spacecraft to withstand unexpected conditions and continue operating successfully. Reliability engineering prevents spacecraft failures by combining careful design choices, thorough analysis of potential failure modes, extensive testing, autonomous fault management, and strict verification. This comprehensive approach ensures spacecraft can survive and function in the unforgiving environment of space, reducing the risk of mission loss due to mechanical breakdowns or system failures.